Well, welcome everyone today to our latest in our series of sustainability seminars. Yes, it is on. And please sign up on our sheet over here so we can keep track of our attendance at our programs. And we also have a number of flyers you may have seen on the upcoming seminars. We have about 4 or 5 in November. So we may be seeing you here again. Today we're very pleased to have with us Dr. John Abelson, who's Professor of Materials Science and Engineering here at UIUC, and he also serves as the co-director of the Energy and Sustainability Engineering Initiative. Professor Abelson received his BS degree in Engineering and Applied Science from Yale University in 1979 and his PhD in Materials Science and Engineering from Stanford University in 1987. He then joined the Department of Materials Science and Engineering here at the university in 1988. He's active in the Materials Research Society and is a fellow of the American Vacuum Society, and he's been a consultant for a number of different corporations. His research interests are in developing novel synthetic methods for thin film materials that are used in advanced microelectronic and engineering applications. And his group carries out fundamental studies and collaborates with other groups in chemistry, electrical engineering, mechanical engineering, and physics, as well as with industry, to evaluate the performance of the devices that incorporate these materials. So please welcome Dr. Abelson.
Nancy, thank you very much. In the bio where it mentions that my research involves collaborations with colleagues in other departments, it indicates the extent to which I've embraced the value of interdisciplinary work. And in fact, in recent years, that has led me and colleagues to create a graduate certificate program which is engineering-wide, covering the energy and sustainability topics. And today I'm going to speak to you about some essential results from a class that we invented called Materials Selection for Sustainability. Let me start here in a rather light-hearted way, just pointing out the role of energy in our lives, joules, the unit of energy, and in fine print, living the good life. And indeed, whether or not you completely admire it, our lifestyle is enormously dependent on major fluxes of inexpensive energy, which of course leads to problems. This is a bumper sticker that I photographed recently, right? Energy supplies are large, but the cost of getting them slowly increases as we tap out the easiest sources, and so there's a lot of wishful thinking about making this process easy, which it isn't going to be. So I have taught several cycles this particular class, Materials Selection for Sustainability. So over the course of the next 50 minutes, I'll explain to you what that really means and how we can use it. You'll actually emerge from the lecture with an appreciation of how we can move forward with improved designs in engineering systems. The basis of the course is this fabulous book, Materials and the Environment, by Michael Ashby. Any of you who have been involved in mechanical engineering, you know Ashby. He's been publishing for the last 50 years and has actually clarified the thinking in many, many domains. So you've probably heard of Ashby creep diagrams and so on. He's now writing the second edition of his book, and my class is pilot testing it for him. So that's really fun. One other introductory comment, just to set the stage. This is from the book. This is a schematic bar chart from deep prehistory to present, showing the fraction from 0 to 100% of non-renewable materials that societies use. So what does this mean? In the prehistoric age, we were not mining and refining materials. With the exception possibly of prehistoric sites for mining flint, which was very good for tool edges. There are some examples in the UK. But practically everything was at ground level, right? This was wood, bone, rocks, mud. And as time goes on, and here we have indicated some of the key developments, Industrial Revolution, cast iron, concrete, aluminum, high-tech metals, polymers, and then eventually silicon-based communication, we've moved up and up to a level where 90-some% of what we use is all synthetic. There is the issue of what renewable does and doesn't mean. It comes out of the ground, but if the amount accessible from the ground is huge, it's technically non-renewable, but not an immediate concern. Nonetheless, there are lots of technologies you've heard about, hybrid cars and wind turbines, whose motor generator sets use rare earth magnets. And when you try to expand up, ask, can we run a society with hybrid or electric cars? Can we power society to some extent with wind turbines? And you multiply up, the quantity of rare earths you need becomes rather large compared to the supply. But today, what I really want to focus on is, what does the material scientist do? What's our role in energy consumption? We'll see a couple of examples, and I'll explain some methodology. So first, we'll start with a quiz. So this is a bottle of an imaginary spring water, Alpure water, invented by Mike Ashby. So here's what we're going to do. Here's this bottle, right? We're going to synthesize the polymer, then we're going to mold it into the shape of the bottle and, of course, the cap. We'll take the empty bottles, we'll fill them with French spring water, we'll drive them 550 kilometers to Cambridge, England. We're going to refrigerate it and serve it to Mike Ashby at lunch, at high table, and then recycle the bottle. So my question to you is, filling itself doesn't require much energy, right? But in terms of these others, where is the big energy hit? So I'll call for some votes. Now, by the way, everyone agrees that recycling is good, so we'll come back to that. We're going to make the polymer, mold it, ship it, and refrigerate it. Those are your four basic choices. How many votes for synthesizing the polymer being the big energy cost? How many votes for molding it, which is a thermal process, molding it into a bottle and cap? Okay. How many of you think that shipping it to Cambridge in a truck is the big hit? And how many of you think refrigerating it matters? So you're a good audience, because a year or two ago when I did this quiz, everyone would vote for the truck. They said, brain dead, driving it in a truck, 550 kilometers. So it turns out if you do the analysis to about 1 digit of precision, it turns out making the polymer, synthesizing the polymer in this example is the big hit. You know, these polymers are directly derived from fossil fuels. So you are, by the way, not burning the polymer, right? You're not releasing all its CO2 to the atmosphere. But this thing is basically made of fossil fuel. Making it into a bottle is there, but not enormous. It turns out, if you load an 18-wheel truck, even though it seems crazy to drive water from France to the UK, the energy hit's about that big. This is the refrigeration. Putting the stuff in the refrigerator and cooling it down for a day or two is more energy than it took to drive it from the French Alps. And we can convert this into the equivalent carbon dioxide emission, and these are both for 100 bottles. By the way, there's a credit over here. This represents the credit that the next person would gain if you could recycle the polymer. In other words, this negative figure represents energy you would not need to commit to reuse that polymer. You do commit some energy to collect it, chop it up, soften it, and reprocess it. I will later explain where these little charts come from. They actually come from a piece of software that Ashby and Company have created, which is very powerful. Well, one point, I may be preaching to the choir here, is how do we compare choices? So we talked about a bottle. Here are a variety of familiar bottles made with a variety of familiar materials. So if I push the button and say, look, if you're an energy person, we should talk about the energy consumed to make these materials. Here is the energy to make 1 kilogram of polyethylene terephthalate, polyethylene, glass, aluminum, and steel. So you look at this and you say, glass is the winner. I love glass. But will glass be the winner? So the question is, really, per unit of function, which is holding liquid. So an aluminum can, you know how thick the walls are in an aluminum can, right? You can just crush it in your hand. How thick are the walls on a glass container? Right? Much, much thicker for mechanical reasons. So if we convert this plot into the energy of material needed to make a bottle to hold 1 liter, this is now the comparison. So glass, which was here, jumps way up simply because of the necessary wall thickness. Interestingly, our all-time winner is steel. This is steel with a very thin lacquer coat to make it not corrode. And steel is recyclable. It turns out in this study that our friend steel comes back several times as a surprising winner. However, there is one other property not listed on the slide which makes glass different from all the others. Yes, and, well, material source, right? The Earth's crust is largely made of SiO2. But the ability to reuse the bottle. These other containers, right, the way they're designed and made, we can't consider reusing them. Glass could be washed and reused. Now, of course, there's an energy cost for collecting and washing. But even today, if you want, you can go to a store and buy Oberweis milk in a glass bottle. So if we could reuse this container, let's say 10 times, and the energy to wash it wasn't that large, you could imagine this bar dividing by 10, or a little bit less, because of the washing cost. Right? So we encounter immediately important issues which are as much sociological and system issues. The materials person knows what the material can do, but I can't guarantee how often this glass would actually be collected and reused. If we do the same sort of analysis across a wide spectrum of familiar systems, airplane, car, refrigerator, this is British, so car park means parking garage, private house, and carpet, we see a great deal of variation between how much energy is needed to make the materials or manufacture the product or transport it to market, and how much energy is required to use it. So on the top, we have things that move, the airplane, the family car, and things that are primarily heated or cooled, in this case, the refrigerator. And the use bar completely dominates. Whereas for things that are largely stationary, so the parking garage is completely dominated by the materials content. It has a little bit of use energy, and this represents lighting, perhaps a fan, right, to pull car exhaust out. The private house is the one example which may be approximately balanced, where the what we call embodied energy in the materials is comparable to the use energy. Something like a carpet, no surprise, the materials content is large. What's the use column doing here? Right? Is carpet sitting on the ground? How's this thing using energy? Vacuuming, and then occasionally when you bring in the carpet cleaning people, that truck sits outside, right, whirring along. People are sometimes surprised by this bar, and I point out to them, the airplane is a flying fuel tank. If you think of your last flight to Europe, for example, sometimes the pilot gets on and announces the takeoff weight, and you listen carefully, right? And you realize that by the time this 747 or 777 lands in Europe, it will have burned off like 500,000 pounds of fuel. And you think, 500. And then you realize, well, how else did this thing, with 300 people on board, leap into the sky, go 5 miles high, go 550 miles an hour, and cross to another continent. Right? So I point out to students in the class, I say, now let's suppose that I could come up with a new generation of superalloys for the turbines, the turbine blades and the engines. And the whole thing here is to make it run hotter. Now suppose, in making my next generation superalloy, I had to invest considerably more energy into making those blades. And the net result was that the airplane was 1% more efficient in flight. Would you do it? And the answer here is, you bet you would. You dump a bucket load of energy into making the engine if you could make it even 1% more efficient. Because over the lifetime, that's 1% of this bar. And the comment here is related to the question of life cycle analysis. It's very easy to encounter life cycle analyses where the viewpoint, that is the input and output gates, surrounds one piece of the process. For example, I go to Boeing. I draw a mental line around the Boeing plant, and I say, how much energy do you use? That viewpoint would lead you to say, well, boy, you better not, up your energy consumption by a third fooling around with these engines. But you'd have the wrong answer. The LCA must surround the entire question of system use. Now, what do we do in the class? How do we approach this? The Mike Ashby and a software house, which has been around 20 years now, had long since had a database of materials properties for engineering. What they've done in the last 10 years was to put in what they call eco-data, derived from a variety of sources. There's a lot of interpolation. It's actually done with a careful statistical method to look for data that are outliers and not accept it naively. So let's have a look. Here are data for our friend aluminum, right? A very big engineering material. So we can see, for example, the known reserves in the Earth's crust. That's not the total amount that's there. That's the amount we know about that we could go and mine, right? That's not the total resource base. That's the reserves we've identified and the annual production. What I want to draw your attention to is how much energy does it take to take aluminum ore, bauxite, this right, white powder, and turn it into aluminum. So the current range of numbers is around, the average is about 220 megajoules per kilogram. So how do we think about that? Let's take a familiar unit of energy, the kilowatt hour, right? Here's your toaster. It's 1,000 watts. You turn it on, click, gets real hot, and you leave it for an hour. That costs you 10 cents. That is 3.6 megajoules. So we're talking here something like 70 kilowatt hours. So turn on your toaster, click, let it run for 70 hours, and you've now paid the energy to have a 1 kilogram block of aluminum in your hand. So it's not overwhelming, but it's not small. Aluminum is one of the bigger ones. Steel is only about 30. Now, people often think about, well, there's the energy to shape things. Suppose we cast aluminum. You think, oh my God, I have to melt it, bring it up to temperature. The casting energy is about 2.5, whereas the energy to get it out of the ore was 220. So you can see that the thermodynamic energy to get it to stop being an oxide and be a metal, plus all the other energy inputs, is that much larger than just melting the stuff down. And the energy that we have to invest to recycle is about 20, which is only about 10% of this extraction energy. So with aluminum, high extraction energy, not too enormous recycling energy. This is why the drive's so big for recycling. Now, this is the longest slide. I have to lay out the steps in how would we figure out our problems. This is phrased in terms of, suppose we were designing something or redesigning something. So consider a proposed object or system. What do you need? So you need a preliminary design that achieves the function, right? I'm building a bridge. I'm building a race car. I'm building a solar thermal tram wall, right? Okay? And sets necessary constraints, right? How big, how stiff, how heavy, whatever, how much thermal conductivity, whatever the constraints need to be. And I break it down into its components, and now I have to say, in engineering terms, what do I need? And here's the interesting part. You need a methodology, which I'll show you in a moment, to calculate a figure of merit for each component. How would one material work versus another? So it turns out you almost invariably end up using certain ratios of properties. Occasionally use single properties. A lot of things are ratios. Once you've done that, can we also convert the figure of merit into an ecological implication, like embodied energy, CO2 footprint, even water consumption? And then trade off, because in part 3 you were an engineer saying, okay, I'm making this as light as possible. And in part 4 you were an ecological engineer saying, hold it, let's keep that embodied energy down, or keep that CO2 footprint down. And these will not, in general, have the same solution. So what do you pick that makes you pretty good in both? And finally, we've already seen examples. We need a method to estimate in advance what a life cycle cost would be. Traditional LCAs are done on already existing systems that have been functioning. So you analyze after the fact what you did. But for design purposes, to move forward and make progress, we have to anticipate to maybe 1 digit of precision. Right? Is this new design really greener than the old one? Now, even if the numbers we have available only have 1 digit of precision, if we're going to make a difference, our new designs have to be not 5% better than our old designs, not 10%, but like a factor of 2, or at least a factor of 50% if I'm going to bother, right? So we will be able to make precise decisions with less than perfectly precise data if the difference is big enough. So lots of you are engineers, right? So this will be fun. Let's consider, maybe you're ready to build a bridge. So you have beams and they're going to bend. So here are some different things. A rod in tension, a beam, a bar in bending, or if I'm clever, a I-beam, I for Illinois, I suppose, I-beam in bending, or actually a sheet in bending. And what I'll be interested in this example is the stiffness. I press on it, and how far does it deflect? So here's what we'll do. The nutshell story. We defined the fixed parameters, like how long is the beam. But I may not have fixed in advance what we call the free variables, like the cross-sectional area. So we anticipate I could use a material that's really, really stiff and really dense with a small cross-section. Or I could use a material that's a lot less stiff and a lot less dense. It would have a bigger cross-section. So my beam has the same stiffness when I load it, but I've used either a massive stiff material or a not very massive, not very stiff material. And we need to know which one comes out ahead. So, sorry about all the equations, but here it goes. We know how much it weighs. That's the volume times the mass density. Very good. And we look up in our mechanical engineering books the stiffness, and it's these collection of figures. E is the modulus, that's materials parameter. So here's what we do. I have area in the stiffness equation. I also have area in the mass equation. Now I said the cross-sectional area I could vary within limits. So let's ratio it out. And we end up with a single equation by putting this together with these the mass equals this bunch of constants. So the first two terms are things that are predetermined. It has to be a certain stiffness, has to be a certain length. C is a constant depending on how you put the load on it, distributed or 1 point. And everything having to do with the material pops out at the end. Mass density divided by square root of the stiffness, which is the Young's modulus. So what does this mean? This is the material's parameter. If this number is the same, very dense and very stiff, not so dense, not so stiff, my beam would have the same mass. But again, the cross-sectional area would change. By the way, if you do this for various situations, it turns out different parameters pop out. For stiffness, if it's just tension, it's 1 over this modulus E. If it's a beam, there's a square root. If it's a panel in bending, it's a cube root. So all of this just comes out of the mechanical engineering equations. If it's strength limited, you get first power, 2/3 power, 1/2 power. Okay? We could minimize the volume using these metrics, minimize the mass using these metrics, and I'll come back to the others. So let's look at a plot. The database has 3,000 materials in it. So if I put each material in, this looks like an interesting night sky of little points. So different classes of materials, all the typical metals fall in this range, all the typical high-performance ceramics, composites, natural materials, wood, bamboo, so on, polymers, elastomers, foams. So they fall in these regions on a plot of the stiffness, the Young's modulus, versus the density. It's a log-log plot, and that means that if our defining equation has a power law in it, that turns into the slope on the plot. So if I am just trying to find something for simple tension, I just look at rho over E. Here's a line that has a slope of 1. Everything on that line has the same performance, the same final mass. If I look at a line that's higher up, it's better. The mass would go down. So in designing this, I pick a line that's relatively high in the plot, but which cuts through a selection of materials that are all worthy candidates. And then I proceed to select winners based on additional criteria. But you know, if it's not just a beam and tension, suppose it's a plate being bent or a shell, the fact of the power law changes the slope a lot. And now the winners and losers change. So, in fact, you often see things that are shells or large flat shapes, and they're made of things like plywood, or they're made of things like stronger surfaces with a foam core. And that's because this line, with this slope of 3 corresponding to this power law, if you bring it down, what you intersect are foams, natural materials, and composites. You don't get to metals for a long time. They're not as good. But if your object is to put something under tension, you never get to foams. And you might just barely nick into a piece of wood parallel to the grain. But metals win. So depending on what you're doing, the same materials are well adapted for one situation, in this case mechanical loading, and very poorly for another. So this is the power of putting the appropriate parameters on a log-log plot and having a performance index that tells you where to look. Now, we previously had mass density. That was rho. If you have reliable numbers for the embodied energy in, let's say, joules per kilogram, or the CO2 footprint, kilograms of CO2 released per kilogram of material you made, all you do is multiply the mass density in the previous equation by one of these numbers. Now you have a new world, stiffness per embodied energy, or stiffness per CO2 emitted. So let's redo the plot, now wearing our environmental engineer hat. Here it is. and now we have more specific materials indicated. We still have lines with these slopes, 3, 2, and 1. This one is embodied energy, but the winners and losers have changed. Because now, previously my criterion was which beam or shell would be heaviest, or lightest, I should say. And here the question is, which one will have the lowest embodied energy? Here now, a lot of the natural materials turn into the winners because they're grown by sunlight. The energy invested to cut down a piece of wood, dry it, run it through a lumber mill is really peanuts compared to the energy required to come up with a piece of aluminum. So, in technical terms, this is really cool because you now see what all the materials do and you see where you'd want to end up. And the database, the CES database, has all these numbers, and its plotting routine allows you to input anything versus anything. And I'll show you an example later for architecture, where we come up with the variables that matter for a particular problem and plot it and do the trade-off. So let's do a little example. Suppose we want to save fuel in an automobile by making it lighter. Okay? Automobile is something that moves. A lot of fuel consumption is associated with acceleration because you have to put the kinetic energy, 1/2 mv squared, into the car every single time you accelerate from a stop. So let's take a kind of low-level example. Let's suppose the car originally had a piece of steel as the structural part of the bumper, front and back bumper, 20 kilograms total, and we want to replace it with something else. It's a toy example, but it's very illustrative. What's the function? It's a beam subject to bending. So from top view, this might be the frame, and we're going to imagine an object hitting the bumper. I need a certain yield strength, and I want to minimize the life cycle energy. And I'm going to do that by minimizing the mass. But now, if I replace it with steel, it does not have a very big embodied energy. If I replace it with something else, maybe you're a fan of high-tech composites, the energy cost of making the composite is quite a bit higher than steel. But it'll lower the mass, so the car will use less fuel. So it's a trade-off. So first, we ask, well, in an empirical sense, how much does mass affect fuel consumption? Here's a bunch of plots. These are European cars. I point this out because there are not so many Skoda Fabias or Vauxhall Corsas driving around in Urbana, but nonetheless, from an average point of view, Ashby draws a line, a least squares fit, through the center of the plot. You could always say to me, well, this includes some fuel-inefficient vehicles. Maybe your line should be through the lower edge of the plot. In any event, we draw a line through and we extract what the energy consumption in megajoules per kilometer would be versus mass. Okay? And a car of interest might have a mass here, say it's 1,000 kilograms. So we're going to work up and down this local slope. We're going to improve our Vauxhall Corsa. For purposes of time, I'm going to skip the messy equation that comes in. What we do is we say, consider the mass of a steel bumper to give a certain yield strength. Consider the mass of something else to give the same yield strength. And since I used that much of it, what is its embodied energy? So here we go. Here's the trade-off plot. 0, 0 is where we started. A not enormously strong run-of-the-mill steel. Now, I could substitute it, and the embodied energy might, for example, go up. And most of these are on the upside. So that's a loss. On the other hand, my candidates are lighter than steel. So over 200,000 kilometers, 120,000 miles, the car is a little bit lighter and uses a little bit less fuel. So this is a gain, this is negative, and this is a loss, this is positive. I can draw in a bunch of lines which are the sum of the two. and this is how much I would save. Up here, 0, I don't save anything. The aluminum bumper saves fuel, but has a big embodied energy. And so when you sum them up, you're staying on the 0 line. Well, so much for aluminum bumpers. I could pick titanium, and that has a significant embodied energy also, and it's a bit lighter, so that's good. But the next plot will show that the cost rules that out. Now I come down here to the sort of things that Amory Lovins and others say, right? High-tech composites. Here's epoxy carbon, epoxy glass, beautiful. They are down near the nose of the curve, which on this is called a Pareto trade-off surface, where we have the most savings. Great, we're probably done. But I do have a question for you. Are those composites recyclable? You recycle a piece of fiberglass? You can chop it up and use it for filler, and that's about it. So if you think about recycling, you think, you know, Amory, it's all good, but at the end of life, we have another issue. So you look around your plot and you say, gee, what's this? This is not quite as good as this one, but it's pretty close. It's an alloy steel with a very high yield strength. And at the end of life, this car with its alloy steel bumper could run right through the chipper and just turn it into a bunch of little flakes and completely recycle that steel. By the way, in Europe, the Renault automobile company, in the last decade or so, switched the manufacturing of their cars. You know, there's the basic floor pan. It's the floor of the car, and then up front it turns into the engine compartment with the support for the springs. They converted all of their production to high-yield strength steels. I don't know if it's this one, but it's similar. The cars are a little lighter. The crash protection rating all went up to 5 stars, and they're all recyclable. So the ecological solution here was not to switch to, wow, a composite like my tennis racket. It was to say, to go back and say, you know what, if we could increase the yield strength of our steel through clever alloying, we get to the same place. Here's the equivalent in cost. The database has cost numbers. Titanium alloys is in the next room. So if you are a military aircraft, titanium is in. And if you are a car bumper, titanium is out. Argonne Labs has their very powerful study with a software called GREET, which you can actually download and use yourself. These are a couple of years old now, but they had estimates for conventional, this is internal combustion engine, conventional car and a lightweight car, in their global view, trying to change as many materials as possible. The embodied energy for the material goes up. The use energy goes down because this one's lighter, right? So we have a net savings, but I don't know how recyclable it is. So I have to go talk to the Argonne people and learn what they say. Now, I alluded to this earlier. This is a little segue. Life cycle analysis performed after the fact is fine, but if I'm sitting here trying to design something, right, I need feedback now. So what this particular database has is what they call the Eco-Audit tool. It basically says the database has numbers for embodied energy, mechanical properties, and we'll also put in numbers for the typical energy to ship something by truck, ship something by ocean-going ship, and so on. Let's put it all in. So the spreadsheet allows you to just say, okay, what's this thing going to be made of? I'm going to use this material. This is how I'll make it. This is how much. Can I or can I not recycle it? And you keep adding stuff, right? So for an electric tea kettle, for example, it's intriguing. This is the list of materials that's in the tea kettle, including, by the way, the packaging to ship it from China. So you have this whole bill of materials, and the database knows the embodied energy and the processing energy. Well, let's see. It was made in China, so it went sea freight, right, in containerized cargo, to the West Coast, then it went on train or 18-wheel truck. You can put this all in. The database has the typical number. Everything here is good to 1 digit of precision. And if it uses energy, maybe it's electrical, maybe it uses a liquid fuel, you put that in, you know, how much time per day is it on? How many years does the thing live? And out pops data in whatever form you want, including the bar graphs I've been showing you. So here's our tea kettle. This is shipping it from China. This is all those materials, making it, and this is using it. It's plugging the thing in and using electricity to boil the water day in and day out. That's the big energy hit. So I would certainly love to be consuming fewer materials and less energy. But from this perspective, if energy is the perspective, our focus has to be on reducing that. So what do we want? A better insulated tea kettle? Maybe a tea kettle with a better level indicator. So if you need 1 cup of water, you fill it with 1 cup of water. Because if you're always, because, quote, it doesn't matter, filling it with 2 cups of water, you've doubled the bar here, basically. I will wrap up with a comment about architecture. And some of you will recognize this picture. This is a house in North Urbana called Equinox House, built by Ty Newell, who's a retired professor of mechanical engineering. He's worked on solar and thermal problems his whole career. This house actually is, it's extensively monitored, net zero in use energy. Averaged over the year, it's truly net zero. And in back, he actually mounted his photovoltaic array separately, although it could go on the roof. And that's what generates electricity. So intriguingly, this is a solar house, but it does not have big windows facing south. So how can that be? So it turns out when Ty Newell works through the design, it turns out if you make a lot of windows facing south, you gain a lot of heat and you lose a lot of heat. So even a very high performance window, averaged, is really only about a 5% efficient device. The solar cells in back, are about a 14% efficient device. They're driving heat pumps with a coefficient of performance between 2 and 3. So they, in effect, have a real efficiency more like 25%. And at today's prices, 1 square foot of triple pane glass is about $35, and 1 square foot of solar cells is also about $35. So Ty Newell, who spent 30, 40 years working on solar thermal, now says, I'm prepared now to say that solar thermal is not the way to go. He's designed a variety of houses. This one has a more unique look. The other ones look like totally regular houses. So how does this work? They're super insulated. So the heat loss is very low, and we use heat pumps and air exchange to take care of conditioning. But let's see what's inside. This is during construction. It's built not conventionally. It's built by structural insulated panels, which are wood faces and styrofoam core. So these are made in a factory and shipped to site, precisely sized for this house, right? So the foam in here is almost a foot thick. And you stand these things up, and you nail them to the footer. And it's sort of like assembly by numbers. You keep lifting these things off the flatbed truck, and you screw them in place, and not too many days later, the thing is done. Then, of course, you wrap it, and you have siding and roofing. But you'll notice the 2x4 framing has disappeared. What are the trade-offs? Well, we've reduced the use of wood, which is, by the way, supposedly a renewable material. A conventional house we might insulate with fiberglass, which is not too enormous in embodied energy. And here we use styrofoam, a lot of it, like 4,000 cubic feet. And it's derived from fossil fuels. So how do we end up in this thing? How much is worthwhile? So let's do a little calculation which is very indicative. We need some local data. We need an integrated number per year of the number of degree days of heating or cooling. So when the outside is significantly hotter or significantly cooler than the inside, this is the temperature difference across the walls, and we're going to have to either heat or cool to compensate, right? You read in the newspaper about, how many degree days this month. And now, very critically, we have to assign the lifetime of the structure. So let's say 100 years. So what the math reveals. Styrofoam has an embodied energy that's about 16 kilowatt hours per pound of foam. So I use kilowatt hours because this is, again, like your toaster. I'm going to turn on my toaster, click, kilowatts running there, and I let the thing run for 16 hours. And at the end of it, I have a pound of foam. Not such a small number. Now, if you run a calculation, see, if you use more foam, there's more embodied energy, but there's less loss because the insulation value goes up. It turns out, somewhat surprisingly, the minimum lifetime energy occurs when the embodied energy equals the energy used in heating and cooling. One plot increases with thickness, the other decreases like 1 over thickness, and if you just minimize the sum, that's the result. It's surprising, but it's only about 2 lines of algebra. And if you write that out, there are 2 equations that are interesting here. The lifetime energy turns out to be, this is the degree days, this is the lifetime of the structure, this is the embodied energy times the thermal conductivity under a square root. So I put in blue the material's performance. The lifetime energy is minimized if I can minimize the embodied energy to make the stuff and minimize the amount of heat leakage that goes through, the conductivity. So it's the product that matters, and I want both of them small if I can. But what about the thickness of the foam? It turns out the same equation tells you the optimized thickness. Here again we have the degree days and the lifetime. Now it's a ratio. I want the thermal conductivity very low compared to the embodied energy. So I want the product low, and I need the ratio low. So we go into our database, and we program in these 2 equations and let it sort through all the materials it knows about. And we get this plot where I have plotted the total energy, embodied plus use. Here is 5 billion joules, for example, versus the wall thickness. So here are all a range of materials which we might consider. Now, some of them are less familiar, but they're in the database. Like paper honeycomb is less familiar. It doesn't have cellulose insulation, but it would be closely related to one of the paper products. But here's some things we know about, right? Polyurethane, polystyrene, right? And these numbers are density numbers compared to fully dense. And we see a plot like this. And way down at the bottom, corkboard. Corkboard has a significantly lower total energy over its lifetime. Hey, that's great! But we should look closely at our plot. It's 1.5 meters thick. Well, we apply a little reality to our engineering here. The point is, cork in the database has a very low embodied energy because it's a natural product. And it has a low thermal conductivity appropriately. So if we were willing to make it this thick, we could really make out like bandits in the 100-year life cycle cost of the building. Now, you need to run the equation some different ways. You might want to use cork, but about a foot thick might be about as thick as you typically accept. So polyurethane here, you'll notice, is very common as a spray-in insulation material. And here it is, and this is dropping down in my toy calculation at about 0.2 meters thick, about 7 inches thick. That's a realistic kind of value. But it has a pretty high embodied energy. It has a decent thermal conductivity, but the combination puts you up here at about 8 or 9 gigajoules of energy over the lifetime. Okay? So we face some fundamental trade-offs, and a big question here is, what's really the lifetime? So let me give you a little example. I took a picture of a new building going up in the corner of University and 5th just last week. Oh, well, I have a little more words here. By the way, suppose you consider polyurethane. Divide this out. This is the total energy, 8,300. That's embodied plus use. At 10 cents a kilowatt hour, half of this is youth. It's $35 a month for operation. Okay, let's go up to University Avenue. You can see this yourself if you drive by. Here is what will be another of these, student apartment buildings. And the steel frame is up and the wall is up. And here they had to put in the electrical box, so they mocked up what the wall construction is like. Here's the tar paper. Here's the external brick. And here is 1 inch of styrofoam. 1 inch. Doesn't sound like the plot I just showed you. And this is calculated to be only enough to pass code and sell the building. By the way, if you go back to the previous equations, a possible way to think about this is you have applied a kind of discounting, economic or mental, to the time here, the effective lifetime. So if the thickness goes as square root of the discounted lifetime, and the thickness is, let's say, a factor of 5 too small, it means in your mind you've discounted the lifetime by the square of that. So from the developer's point of view, a 4-year horizon is forever, not 100. Right? But that building will probably be there for 50. So it's going to crank along for 50 years with that 1 inch of foam in it. Isn't that great? So our conclusions. So we need to identify, by the way, this was all about energy, but I could run all the plots on CO2. You could actually run them all on water footprint. It's all in the database, right? We need to identify with numbers good to some precision we can lean on. How much did we dump energy into the materials? And I haven't talked about the processing, because that's typically small compared to the original materials, versus consumed in the operation. And I need performance indices to guide the selection of materials and end up with the best compromise I can between engineering performance and ecological impact. Always a trade-off. But we can do a lot better than we're doing today. The Eco-Audit tool allows you in spreadsheet form in about 10 minutes to figure out approximately where you ended up. We need trade-off methods. I've alluded to the fact that economic discounting plays a hand. That's a whole other story. And my big conclusion is to be green, to be actually green, requires real numbers and real methods. And today, I've showed you a set that gets you to some answers. Thank you very much.
Questions for John?
But you didn't answer the question of whether Thai used the right materials or not.
You have to assume the 100-year lifetime.
That's a huge assumption.
Yes, it is. Certainly, driving around town, we see a lot of homes that are 100 years old. We also see some that never make it to 100. There's also an end of life question. Are we going to toss away the styrofoam, or will there be a century from now, 75 years from now, any method that makes use of it and recovers some fraction of the embodied energy? So I should point out that on my plot of the total energy use versus various kinds of insulation, there was a curvature there, right? Some are better than others, but all of these are enormously better than not doing the insulation correctly. So if you move away from that optimum, for example, you could say, oh, too much embodied energy. Give me 3 inches, right? What you have done is said, I'm going to drop my embodied energy down, but your use energy is going to go way up. So again, if you just write out these two equations, the saddle point, the minimum, is where they balance, but they balance because you've dropped the use energy so far down. So if I called up the data from this house, you'd see if you shrink the insulation down, the use energy just gets fantastically high. So it's not a stupid choice, but you're asking me, I've done better with the 100-year assumption. Could I do even better? We could rerun this just putting tau in some number you like. 50 years? Or if you're an economist, you say, discounting. By the way, if you discount costs, right, let me just gesture. Oh, we have a word. If you integrate benefit, if you have the sum of benefits per year, if you don't discount, let's say you're saving energy every year, if you don't discount, it's a straight line. Right? Every year I'm not using a certain amount of fuel for heating. If you discount, the integral looks like that, and in the long time limit, it goes asymptotically to the annual benefit divided by the discount rate. And this thing is dying quickly, so it's essentially flat. So if you're not a discounter, you say, hey, look, I'm saving forever. And if you are an economist discounter, then, right, that's the portion you want me to ignore. So, the effective time, no matter how long the physical life of the building, if you're a discounter, and you say the discount rate is 10%, 1 over 0.1 is 10. You're telling me that in the benefit to cost ratio, the effective lifetime is 10 years. If this is 20%, you're telling me it's 5 years. So the example of the student apartment block that's being built, it works out to about 4 years discounted. So the developer has a 25% discount rate. Not necessarily in his mind, but what he's done effectively looks like that.
It's the person who buys the house has the 25% or building.
Yeah.
And doesn't this suggest then that there's like, well, i.e. people are stupid, but that's not a normal assumption. Right?
Yes.
It's clearly a failure here. What's your take on that?
This is, one of the governing issues that in the end, what's consuming energy is the system. But the way we get there is through a very dissociated process. And our colleagues in architecture, like Brian Deal, talk about this a lot. Even in the architecture business, somebody does the structure, somebody does the interiors, somebody else does the HVAC. Even in their own field, they're not talking enough. Let me just tell you one story. As I was lingering to take a picture of this building, one of the guys who was on lift came down, switched it off, and decided to chat with me for a few minutes. So it turns out a different company does a steel frame as opposed to does this wood framing. And he said, well, that steel frame, they set it up, quote, within spec, but they didn't actually get it true and level. So the frame everywhere, he said, we had to spend so much time recutting all our framing to fit this. Because the steel wasn't quite trued up properly. Like extra 15 minutes work for them, well, that's not their problem. They're, quote, within specifications. So the real point is here, the builder and the user are completely dissociated economically. And that's a big problem. And at least in private homes, but I think more generally, energy efficiency does not show up very strongly in the value of the building. It hasn't. So there are various proposals for how to deal with this. Apparently the architecture community, or the planning community, thinks, suppose that the tax rate for the structure, and there's a multiplier on your tax rate. Suppose that multiplier could be permanently set down a little bit if it's more energy efficient. That would mean that no matter who buys it, your annual tax would be lowered. It would be a way of incentivizing a bit. Anyway, that's a whole other discussion about which I'm not an expert. But you're right. We have to get it's systems thinking. In this course, as in our energy and sustainability option, which some of you have sat in, on day one we walk and we say, it's a systems issue. And then somewhere in each class we say, it's a systems issue. And at the conclusion, at the end of the semester, we say, it's a systems issue. Sorry to seem silly, but if you have to take the life cycle analysis has to be the whole thing. The construction use has to be the whole thing. And disposal at end of life should really be somewhere in the equation. And otherwise, we end up at things like this, right? The amount of physical effort to make that foam 3 inches thick, really close to zero, right? I don't know, a few kilobucks to increase the thickness of foam. Nope, can't do it. I'm the developer. It's not my problem. Yes?
I'm interested, does ASB have in this database straw bale?
The straw bale is pretty good. It's like cork. I think it's coming out in the new version.
So you should run that on Ty's house.
Converting over to straw bale.
Yeah.
It's interesting.
Because then you don't have the recycling problem.
No, that's right. Straw bale is interesting. It has really low thermal conductivity. It also has low thermal mass, so it's good for insulating. It's not very good for smoothing out day-night temperature fluctuations by absorbing heat. It's good in the sense of not conducting it through. It turns out the class and I have just gone through the thermal calculations. You can maximize insulation. You can, as a separate parameter depending on the material, adjust the heat storage. So it turns out this, in technical terms, works out as a ratio of the thermal conductivity and the thermal diffusivity, which has the heat capacity in it. So if I'm insulating, I go to one limit. If I'm making a Traum wall where I can pump heat in from the sun and I let it diffuse through over about 12 hours, I actually end up with a different solution. So
it'd be fun for you to put instruments and Julie and Jody's house and see if that actually is the real world.
yeah, sure, would be.
Any other questions? Well, let's then,